Ever wondered about the heart of a transformer? It's the core. The core is not just the physical center of a transformer, but it's also the pivotal element in its functionality. It's typically made of ferromagnetic materials like iron or ferrite, providing an effective path for the magnetic flux generated by the primary winding. But cores aren't one size fits all. There are various types, each with its own unique characteristics. Laminated cores, for example, are composed of stacked layers of thin steel sheets, offering reduced eddy current losses. Then there are toroidal cores, shaped like a donut, which provide high magnetic efficiency. And let's not forget the EI cores, named for their resemblance to the letters E and I, which are commonly used for their ease of assembly and efficient use of materials. So next time you hear about a transformer, remember, the core is where it all starts. Now let's turn our attention to the transformer's vanes, the primary and secondary windings. Picture the primary winding as a coil of wire, directly connected to the input voltage source. When an alternating current flows through this winding, it's like the heartbeat of the transformer generating a magnetic field. This magnetic field then induces a voltage in the secondary winding, much like a pulse traveling through the body. The secondary winding, another coil of wire, is like the veins carrying blood to the rest of the body. It's electrically isolated from the primary winding, receiving the induced voltage and connected to the output load. The strength of this pulse, or the induced voltage, is proportional to the turns ratio between the primary and secondary windings. It's a beautifully symbiotic relationship, mirroring the intricate networks of arteries and veins in a living organism. From input to output, the primary and secondary windings are the lifeblood of a transformer. With electricity, safety is paramount. That's where insulation and tap connections come into play. Insulation, often overlooked, plays a critical role in every transformer, preventing short circuits and ensuring safety. The wire used for windings is typically insulated using materials such as enamel, paper, or plastic. These materials are chosen specifically for their ability to withstand the high voltages present in transformers. Now let's shift our focus to tap connections. Ever wondered how transformers adjust to variations in input voltage, or how they provide different output voltage options? The answer lies in the tap connections. These are essentially multiple points provided on the winding, enabling the transformer to adapt to fluctuating voltage conditions. So, whether it's the insulation providing a safety barrier against high voltages, or the tap connections offering flexibility in voltage adjustments, these components play a vital role in the efficient operation of transformers. Insulation and tap connections, small components with big responsibilities. A transformer is more than just wires and cores, it also needs protection and cooling. Delving deeper into the components of a transformer, we encounter the tank or enclosure. This protective shell shields the transformer from environmental factors like moisture, dust, and mechanical damage. Additionally, the tank houses insulating oil, which aids in heat dissipation and provides an extra layer of insulation. Now let's talk about heat. Transformers generate heat due to losses in the core and windings. This is where the cooling system steps in. Whether it's fans, radiators, or oil circulation systems, these cooling mechanisms work relentlessly to dissipate heat, keeping the transformer's temperature within safe limits. The last piece of the puzzle is the bushing. These insulating devices connect the transformer windings to external circuits. They maintain electrical isolation, provide mechanical support, and seal out moisture or contaminants. Protection, cooling, connection, these are the roles of the tank, cooling system, and bushing. Last, but not least, let's talk about the transformer's lungs and oil regulator, the breather and conservator. The breather, an often overlooked component, plays a vital role in the longevity of a transformer. It regulates the air inside the transformer and, most importantly, prevents moisture from entering. Picture this, it's like a gatekeeper using desiccants to absorb moisture from the incoming air, thereby ensuring a dry and healthy environment for the transformer. Now let's shift our attention to the conservator, the transformer's very own oil regulator. In larger transformers filled with insulating oil, maintaining a constant oil level is crucial. The conservator, acting like a reservoir, is connected to the transformer tank via a pipe. As the oil expands and contracts with temperature changes, it moves in and out of the conservator. This ensures a consistent oil level, keeping the transformer functioning at its best. And so we've breathed life into our understanding of transformers from the core to the conservator.